Hi everyone, welcome back to codeAYD. Today we're going to be talking about logic gates. So there's three main types of logic gates: the AND gate, the OR gate, and the NOT gate. And from these three gates we can build the other gates. So what an AND gate does is it takes in two input sources, A and B, and then it has an output source, S. Now we normally remember it as A times B equals S. So for example, if they were both off, A and B, then S would be off. And if one of them was on, but the other was off, it would still be off. In order for S to be true, or the output to be true or on, we need to have both inputs on, and that's why it's called an AND gate. The OR gate, on the other hand, only needs one of the inputs to be on, but also they could both be on. A NOT gate is perhaps the simplest of them all. All it does is it switches whether or not the signal is on or off. So for example, if we gave it 0, it would return 1, and if we gave it 1, it would return 0. Now we can combine these gates, such as AND and NOT, and we get a NAND gate. A NAND gate is the opposite of an AND gate, so it takes whatever an AND signal would have been and then switches it. It's just an AND gate and a NOT gate put together. So for example, it would always be on unless both input sources are on, then it would return false, or 0 in this case. Now we can combine the OR and the NOT gate, and we get a NOR gate. A NOR gate is the same as an OR gate, except it's inverted. So if they're both off, then it returns true, but if there's any other circumstance, then it's off, as you can see in the table. So now that we have these gates, what we can do is we can add up numbers. So if we add, for example, 23 and 127, we can see how a computer would use these logic gates in order to give us our solution. Now I'm sure most of us know that a computer isn't going to read 23. It needs to be converted to binary. Whilst it's not the focus of this video, it's important to know how to convert it to binary. So for example, 23 is not bigger than 128, it's not bigger than 64, it's not bigger than 32, but it is bigger than 16. So we put a 1 at 16, and now we have a remainder of 7, because that 23 minus 16 equals 7. Now 7 is not bigger than 8, so we put a 0, but it is bigger than 4. So we put a 1, and we subtract 4 from our remainder, so our remainder is now 3, as you can see. 3 is bigger than 2, so we put a 1, and our remainder becomes 1, because we subtracted 2 from the remainder. And 1 obviously fits into 1, so we have a remainder of 0. And whenever converting to binary, we will always end up having a remainder of 0. If not, we've done something wrong. So now we have 23 in binary. And we just need to convert 127 to binary in order to add up these numbers with logic gates. So 127 is not bigger than 128, but it is bigger than 64. Now our remainder is 63, which is bigger than 32. 31 is bigger than 16. 15 is bigger than 8. 7 is bigger than 4. 3 is bigger than 2, and 1 equals 1. So that's now 127 in binary. Now it's not just a matter of adding them up like we would add normal numbers, because we would get 2's in here and computers don't understand 2's. So we need to use transistors. Now a transistor has 3 pins on the bottom of it. 2 of them are input and 1 is an output. And if we zoom into the transistor, we can see how it works. We have a semiconductor at the bottom, which is normally silicon, and we have 2 conductors that are represented here in gold. Now if we put in the pins from the transistors, we can see how it works. So if we color code them such that they're orange and pink on the outside, we can add in our 3rd pin, which we'll wrap in an insulator, and this is called the base. When it is on, it allows current to flow from the collector to the emitter. Now a logic gate works by putting 2 transistors and connecting them in a special configuration. If we set the base of the first transistor to be on, then we can see that current can flow from the collector to the emitter, and the light bulb turns on. If the second transistor is on, then we see that current flows from the collector to the emitter of the second transistor, and the light bulb turns on. And this also works if both transistors' bases are on. And so now we've built an OR gate. Now we can connect one transistor to the next transistor, which connects to the bulb, and we can see what happens here. If we turn on the base of one of the transistors, the current flows to the next transistor, but because that transistor's base is off, the light bulb does not turn on. And if we tried it the other way around, The bulb does not turn on because the second transistor is not being given a current to give to the bulb. So the only way for this bulb to be turned on is for both transistors to have their bases turned on. And this is now an AND gate. Now to add up numbers, we're also going to need an exclusive OR gate. An exclusive OR gate acts just the same as an OR gate, except it doesn't work if they're both on. It has to only be one of them. Now, one of the ways we can represent an exclusive OR gate is by combining logic gates that we already know. An OR gate, a NAND gate, and an AND gate would be able to do this. The AND gate is what we'll look at first on the right. It needs the two other conditions to be true, which is that both of the transistors are not on and that one of them is on. And that's basically how an exclusive OR gate works. But how exactly does a NAND gate work? Well, we know it's an AND gate and a NOT gate. But what is a NOT gate and how does it work with transistors? This simple circuit explains it very well. The issue with a NOT gate is that when there is no input coming in, there needs to be output going out. But where is this power coming from? Well, quite simply, we have to make this circuit. This in the middle is a transistor, where the arrow is the emitter and the circle is the collector. The thick line in the middle is our base. When the base is turned on, current will pass from the circle to the arrow, but if it's turned off, this won't happen. And here's some examples. The top will always be on, and we can see a resistor there as well. So when the input is off, we will get an output. But if the input is on, that means the transistor is open, which means that some of that current from the positive terminal is able to flow to ground. So even though the outward signal is not 0, it's not 1 either. So that means instead of having 0 and 1, we'll now have 0.5 and 1 in a NOT gate. But a computer doesn't necessarily use zeros and ones. It uses high and low frequency signals. And so because of this, it will be able to know that 0.5 is really 0. And that's how a NOT gate works. And once we have our NOT gate, we now know how our NAND gate works. So now we can add up the numbers. This here is called a half adder. It's built up of an exclusive OR gate and an AND gate, and as we give it different signals, we'll be able to see results. Again, if we expand the exclusive OR gate, we can see how it really works. If we turn on the top signal, for example, our result is 0, 1. If we turned on the bottom signal, our result would be 0, 1. And if we turn them both on, our result would be 1, 0. Now this makes perfect sense, because 0 plus 1 equals 1, 1 plus 0 equals 1, and when they're both active, 1 plus 1 equals 2. And in binary, 2 is represented as 1, 0. This is half of an adder, but it's only half. We need a full adder. So to do that, we're going to remove the ends of the adder, and we're going to need 2 of them. Now to make it a full adder, we'll also need a carry-in wire and a carry-out wire. And this will all have one result at the end, as we can see with the 0. This single bit is what the full adder will do, as well as being able to influence the next adder. So that's one full adder. But because we're adding up 8-bit numbers, we need 8 of these. So we can turn it on its side, add in 8 more, and we can see how the system will add numbers. If we put in the numbers in binary, which we used from before, we can now add up these numbers. We'll start with the first digit on the right. 1 and 1 results to 0 in this case, but 1 and 1 in the next digit results to 1. And the reason for this is that it was influenced by the carry-in wire from the previous full adder. We can continue this the whole way along, and you can pause if you like to see the patterns of the adders and see how they're all working. We'll continue this along, and we have our number. This binary number is now our result. If we assign it the numbers we had before, and we remove the zeros, then we can add up these numbers and get our result, and we can verify it in decimal. 23 plus 127 equals 150, and now you know how a computer does it with logic gates. That's all there is to logic gates. Thank you.